This video was created for an Introduction to Physical Oceanography taught at the University of California, Los Angeles in the fall of 2020 by Andrew Stewart, Jordyn Moscoso, and Clara Si. In this video, we will be exploring the equation of state, which helps us understand the density structure or stratification in the ocean. We will begin by considering the linear equation of state, where ρ is the density of water, which depends on both the temperature of the water, denoted by T, and the salinity, denoted by S. Because there is no exact form of the equation of state in the ocean, we use approximations like this one to help us better understand the density structure. Note that not only does a parcel of water depend on the local temperature and salinity, but it also depends on a series of reference values, including a reference density, a reference temperature, and a reference salinity. These are often known quantities of the bulk fluid or other parcels nearby. For this experiment, we'll be using a reference density of 1,000 kilograms per meter cubed, or the density of fresh water. The final components are alpha, the thermal expansion coefficient, and beta, the haline contraction coefficient. Note that the sign in front of alpha is negative, meaning that with increasing temperatures, we have less dense fluid, and with decreasing temperatures, we have more dense fluid. Now we'll get to the experiment, which not only takes advantage of the equation of state and density layering in the ocean, but the differences in diffusion between temperature and salinity. That's why this experiment is also called salt fingers, or double diffusion. For this experiment, we'll use a stationary rectangular tank, a pitcher, 13.5 liters of water about 20 degrees Celsius or room temperature, some food coloring to better see the layers or stratification, half of a liter of water heated to about 90 degrees Celsius, 7 grams of salt, and 2 to 3 foam blocks to prop up the tank. Now we can get started with the experiment. I start by adding 13 liters of room temperature water to the tank. This does not have any salt added. Next, I add a half of a liter of water with a salinity of 10 grams per kilogram or 10 ppt to the tank. Since this is denser than the initial water mass A, it'll sink to the bottom of the tank. Next, I add a half of a liter of the heated water with a salinity of 4 grams per kilogram. This water mass is actually lighter than water mass A. This seems sort of counterintuitive because there is some salinity present in water mass C. However, the temperature of the water makes it so that it is lighter than the water at room temperature. The fun part of this experiment comes from something called double diffusion, which highlights the different rates at which temperature and salinity diffuse or naturally mix between different water masses. Because these rates are so different, we see very spectacular overturning, or things called salt fingers, once water mass C starts equalizing to the temperature of water mass A. Now we can switch to a visual of the tank. So here's the full setup, with the tank itself and the initial water mass added. I have a couple cameras mounted so I can show different angles of this experiment. I start by adding half of a liter of water that's dyed green that has a salinity of 10 grams per kilogram. This water will sink below the initial water mass that's at room temperature with no salinity. Note that the tank is tilted here so it's a little bit easier for me to layer the fluid without mixing too much. Now that we've successfully layered 2 layers of this experiment, I'm off screen now grabbing the top layer of the water, which is again heated to about 90 degrees Celsius and has a salinity of 4 grams per kilogram. We expect this third water mass to initially sit on the surface, diffuse in temperature, and then mix with the water below. Note that this video is about double speed so that we can see this develop a little bit faster. Now we're starting to watch double diffusion happen as small raindrops of salt start to fall through water mass A from water mass C. And now using that second camera, let's take a close-up look at what's going on in the interior. At this point in the video, you can really start to see the overturning occurring, where water mass C is starting to move beneath water mass A via double diffusion or salt fingers. So this ends our experiment. I'd like to thank everybody for taking time to watch. This video was created by me, Jordyn Moscoso, with experimental design and advising by Andrew Stewart. A huge thank you to the Marine Operations and DO Dynamics teams. And a special thank you to you for watching.